Three, two, one. All right. So, last time we introduced the exciting world of matrices, and now we're going to see how we can use it to start solving differential equations. So today we're going to set the stage for what we're going to do. All right. So this is a theory week. This is a week where we build up a bunch of stuff, and it's like, all right. And next week we're going to tackle these fun problems. Okay, so we would like to solve differential equations that look like this. And specifically, not only do we want to solve these systems where we have an independent variable and multiple dependent variables, we want to do it using matrix methods. So like I noted, there are ways of solving these using other techniques, but they got some pitfalls, they got some problems, they're not the best. So matrix methods, they're the key ingredient. So specifically, this system of differential equations I can rewrite as a matrix equation as follows. So here we have our x, which is our unknown functions x and y, the derivatives of them, exactly what you think they should be. A, note, there's only one y term, -1. There's only one x term, 1. No x terms in the top, no y terms in the second. And a f of t term, so note that we've got these functions that depend on the independent variable but don't involve the dependent variables. So we could separate them off as their own term here, plus f of t like that. And there we go. So these are primarily the differential equations we're going to look at. These are referred to as the first order systems of first order linear differential equations. Linear because scaling and adding of the dependent variables is exactly what's going on. And that's it. And as we're going to see as we go through today, a lot of the theory is basically exactly the theory of second order and higher differential equations, but just everything that we've written in terms of matrices. So today is actually not going to be too heavy in terms of okay, how do you go about solving these? What are solutions going to look like? Because it's going to behave exactly like second order systems. Second order differential equations. And I have this horrible habit where I call anything where there's 2 is automatically a system. Even though second order DEs aren't technically systems, but anyway. Okay, so these are the ones we're going to focus on. So the first thing we're going to do is going to look at what we did with the second order. Let's clean it up, make it lives a little easier. So we'll look at the ones we're going to call homogeneous. And again, this word maybe having a completely different meaning, but in this case homogeneous meaning that there is no plus f of t. The only things in the equation showing up only involve the dependent variable. There's no other independent variable shenanigans flying around. Okay, and we are going to stress that we really should be writing x of t, but we don't suffer death by notation. We will abbreviate it to this, but we do want to keep in mind that x is representing a column vector of functions, not of numbers. Okay. So, for example, here is a homogeneous system of 3 linear differential equations, where the A is the coefficient matrix, so the terms multiplying the unknown functions, -3 for x, 4 for y, -9 for z, 6 for x, -1 for y, no z, 0, 10 for x, 4 for y, 3 for z, and my x, my column vector involving my unknown functions x, y, and z, and my x prime representing their derivatives. All right. There we go. So, just as we did for second order differential equations, we'll focus on talking about homogeneous systems first, and we'll see that this is the thing you would always solve first, and then the general problem ends up being just, do this first, and then you do this other thing. Okay. So by a solution vector, so we're going to be very careful about some language use here, will mean anything that actually solves the homogeneous system. Okay, so for example, let's say we had x prime is 3, -4, 4, -7. So this is one way we're going to write these systems a lot, where you've got x and x prime, and then you'll just put, you just write out the coefficients like here. Right, if you want to, you can rewrite it like a system, right, with multiple equations, but usually we'll just write it like this for the understanding that this is, right, there's a matrix equation. It's really multiple equations that we've collapsed into one equal sign. So a solution vector, for example, will be the following: 2e to the t, e to the t, and this can be verified by plugging it in and seeing that it works. So if we take the derivative, well, it's 2e to the t and e to the t. And if you multiply it by 3, negative 4, 4, negative 7, so 3 times 2, e to the t, negative 4 times e to the t, and you add those up, oh, conveniently, that gives you 2e to the t. 4 times 2e to the t, negative 7 times e to the t, you add those up, and conveniently you get e to the t. So indeed, plugging in x1 prime into this equation, it works. The equal sign is valid. The derivative is the same thing as multiplying by this matrix. Alright, and there we see it written out in a little more precise detail, the notation there. Okay, so hey, there's an example of a solution vector. So when we want to solve x prime is equal to ax, where those are matrices, well, then what we want are solution vectors, right? Column vectors. Right, in our case here, 2x1s. We won't go beyond the 2x2 case, but you can let your mind extrapolate to larger dimensions. Alright, cool. Another one. So, for the same system, here is a different answer. And hey, note that those are very different answers. E to the t and e to the negative 5t don't really have too much in common with each other, do they? Right, and then again, you can verify it works, take the derivative, and do the matrix multiplication. They will coincide, and that means that x prime, x sub 2 prime satisfies x2 times 3, negative 4, 4, negative 7. And I'm really angry I had to do this. I couldn't make it fit on one line. But, oh well, did my best. Okay. So when you're looking at homogeneous systems, here we see, hey, I've made two completely different solutions. It's a 2x2. I have two different solutions. What do I want to do when I make multiple solutions? Well, I want to scale and add them up. So, indeed, just like second order linear homogeneous constant coefficient systems, differential equations have the superposition principle, meaning that I could scale together solutions and add them up to create new ones. And just like we talked about before, when I do this, I want them to be a true new solution. I don't want linear redundancy, so I want linear independence. When I scale and add, it creates something new. It does not just repeat what I already know. Right, and formally that means that if I get solution vectors, and if I scale them up and add them up and I get the zero vector, that means all the coefficients need to be zero. Okay, so it's exactly what we've seen before and worked with before. But now we have a tool to help us out, to make this move a little bit more smoothly. So before we talked about the Wronskian, when we talked about second order differential equations to check for linear independence, we've got the same thing, but now we've got the matrix language to help us out. If we have n by 1 solution vectors, the Wronskian is the determinant of the matrix whose columns are those vectors, right? So there are n by 1, and I have n of them, so it's a n by n matrix. So it's a square matrix, which means I could take its determinant. So, for example, oh, hey, 2e to the t, and e to the negative 5t, and 2e to the negative 5t. We know those are solution vectors. Slap them together, take their determinant, boom, hey, it's non-zero. And just as before, non-zero Wronskian means linear independence. And again, in this case, it actually will be an if and only if. The before, like I said, Wronskian being non-zero, there are some extra assumptions. In our case, if your determinant is non-zero, then your matrix is invertible, which means the columns have to be linearly independent. So this is an if and only if in this case. And now you may be going like, well, okay, well, we called this thing the Wronskian. We had something else called the Wronskian. Are they different? No, they're not. Right, you're still computing a determinant. They're different in the sense of what the functions go inside. You take your two functions and you take their derivatives. We don't do that here. But it's still the determinant in disguise. Okay. So, what do we have now? Well, we have two solutions to a 2x2 system, a 2x2 homogeneous system. We now know that they're linearly independent. Probably want to call that like, oh, I don't know, a fundamental set of solutions or something. So if you've got a homogeneous system and A is an n by n matrix, a fundamental set of solutions is then a linearly independent set of solutions of the same size. So, a 2x2 matrix, you need to find 2 linearly independent solutions. For 3x3, you need to find 3, so on and so forth. For example, as we just discussed, this homogeneous system has this as its fundamental set of solutions. Nope, thought there was more. Don't want to move that fast. But anyway, yeah. So it's just what we talked about for a second order differential equation. It's just just in a different setting, and we've got matrices that basically kind of help us here, where it's just sort of like linear independence. It's like boom, taken care of. Got that determinant stuff, bro. We're good. Okay, and so to wrap up the story, then. Every homogeneous system has a fundamental set of solutions, and thus the general solution is you scale them up and add them. In the same way that second order and third and higher order differential equations have the same thing. So that means the general solution of this homogeneous system, scale and add them up like that, and there we go. So that means that if I want to solve homogeneous systems of differential equations, it's exactly like what we needed to do for second order and higher, find an appropriate number of linearly independent solutions. Then scale and add them up. And that's it. That's very nice on our end, right, because we already know how to do this. We've done this multiple times. The only thing that's worth mentioning and really pointing out is that when it comes to IVPs, now we need to be a little bit careful. So let's say if I were told that x of 0 is 1, 1. So the first thing to note is that, right, it's not like I get x and x prime or something like that. I get x of 0, and again, this is a 2 by 1, so I need 2 pieces of information like that. And when I plug it in, I then need to solve for C1 and C2, which means, oh hey, we've got a matrix we now have a matrix equation to solve. So there you could do row operations if you want to do it that way. You could, of course, try to find the inverse and solve it that way, however you want to solve for C1 and C2. So the only thing of note here to really go, like, by the way, here's like the one little thing that you need to think about is, yeah, there's this sort of initial condition thing you need to keep in mind. But otherwise, it's not too bad. So then that leads us with the last thing to discuss. Non-homogeneous systems then are going to be ones where we have an F term, so there are appearances of the independent variable outside of the dependent variables we're interested in, and there the general solution is exactly what we saw before. Solve the associated homogeneous, and then add to that anything that solves the non-homogeneous system. Just find a particular solution, add it up, and you're done. So, for example, the system right here, the one we've been looking at for 3, -4, 4, -7, if I had a non-homogeneity of -25t and 25t, then a particular solution will be 55t plus 49, 35t plus 23. Sorry, the numbers are goofy. I picked this matrix because its general solution is nice when you needed the t and the -5t. But to make a non-homogeneous one, making one and getting like a reasonable answer, I had to go to 25 before I started getting like positive integer answers, and of course the integers were like weird, like you're 23, right? Jeez. I'm closer to this number than I am to that one. Yeesh. I don't even really remember when I was 23, to be honest. I was in grad school. I don't really remember. I'll tell you about this next year. But anyway, if you do plug this in, it solves the equation, so it must be a particular solution. And that's it. So there we go. You now have a general solution to this differential equation. We got the homogeneous solution on the previous slide, and then we would just add that to this particular solution right here, and that'd be that. Okay, so like I said before we even got going in here, the theory is just virtually identical. It's everything that we had to do for second order and higher differential equations. The only difference now is that everything is in terms of matrices, but all the key ingredients, just the way it's going to go, is exactly the same. And that's very nice, right, because that means there's less lifting on our end that we really got to do. But now this sets the stage of, okay, well, We know what solutions to the homogeneous look like. How do we find them? And we know what solutions to the non-homogeneous look like. How do you find particular solutions? And as we're going to see, the methods we need to use to find those two, while similar to what we did for second order and higher differential equations, have a lot more ins, outs, and what have yous, and it gets a lot more subtle, and unfortunately, the algebra gets a little bit more, or fortunately, maybe, the algebra gets a little bit more exciting. Okay. So that's going to be our capstone. That's going to be our wrap-up. And we're almost there. We are 2 videos away from completing differential equations. So, all right, I'll see you then for the fireworks display. We're in the end game now.